Salutations, 216ers. This is Professor Kaufman, and what follows will be an overview of Project 4. We'll be working on Chester, a C high level tester. This is a little testing framework that is reminiscent of the ones that you've benefited from over the course of the semester that allows you to type something like make test and get feedback on the correctness of programs. Constructing such things is an interesting endeavor and provides a lot of convenience. Software testing is a very prominent part of a lot of shops that put together code. And it may be that in your initial forays into the software engineering world, one of your first jobs would be to be a software tester. Not particularly glorious, but it does come with the side benefits of getting acquainted with all the things that can go wrong with programs and studying them from the outside looking in to test them, break them, etc. So our efforts here are going to be focused on creating a little system that makes it convenient to run programs rather than unit test individual functions. This will be run a whole program. And that'll give us a chance to explore some of the systems level concepts that we've been talking about in the last few weeks. This includes things like creating child processes, coordinating a child and a parent process. So Chester, the testing framework, is going to run these things, but will spin up child process to do so, needs to be able to wait on them and so forth. Creating various things in the file system, like files and directories, redirecting input and output, and then reading and writing files to evaluate the correctness or lack thereof of tests. So there's a lot that can go into this, and you'll be doing it in C, thankfully, rather than assembly, as was the case for our last project. The project setup is similar to others, and this structure mirrors what we did in our very first project together, where each of the problems that are associated with the project deal with building functionality for part of the overall Chester program, and those pieces eventually are assembled to become an executable that can do what it purports to. I may have a chance here to show you what my solution looks like a little bit, not the code rather, but the behavior of it. But first, I think it's a good idea to just walk through some parts of the spec here. It's divided as usual with a preamble indicating as you download the code pack, which we'll do in a minute, what files you expect to get. There are really only two files that students need to work on directly to create them and as well to fill them in with goodies. This will be the Chester funcs and Chester main source files, which, as their name implies, will have a bunch of service functions in it that operate on data associated with Chester, and then this will contain the main eventually. Let's see, there's a bunch of testing files that are provided, as well as a data directory that has some data that's used during testing and provides sample files. We'll have a look at this fortest.md file. But as well, there's some infrastructure already provided. For instance, one of the things that testing framework would need to do is to be told what tests should I run. That's going to come by way of an input file. This is an example of it. And parsing those input files is a bit of a pain. And so the staff have provided a solution for this. It's in the chesterparse.c file. It's a really gnarly bit of code, and that's on account of it's automatically generated from another bit. You don't really need to know about that. Just have a look in the Chester util file instead and find, oh, there's a handy initialize testing suite function from a file. As one of the makeup problems we plan to put out a little bit later, you can write your own version of this if you want, but for those who are in a hurry, you can just make use of the instructor provided parsing one, which will create a struct out of the contents of that file. So as a quick overview, here is the essence of what goes into one of those testing files. This is in roughly markdown format. And so for those of you who are familiar with this sort of textual format, you'll see, oh, there's a little hash here and a hash space followed by some words means a heading of sorts. And this defines here's one of the tests that's there. When I look at this in Emacs rather than this text right in here, it'll actually show like, oh, this is color coded in some ways that are sort of interesting and allows for like folding and so forth. The little exclamation marks up here and then in here, they indicate a directive in the parlance of Chester, which changes some of the options associated with how the tests are run. For instance, this directive here says within this first test, the program to run is bash, and there's a bunch of arguments to bash here. If that program is run, the expected output is in this little block over here. Expected output is Chester is a tester. The little 3 backticks here and backticks here designate the beginning and end of the output block. And you can see when the bash runs here, it's going to earn this commands like echo Chester is and then echo a tester. This is the output that program would produce, and it's sort of going to match that expectation. The second heading down here is a second program to run, a little description of what's at stake. This time we're just going to run the word count program, but feed it input in this case. So that's another thing you specify in the input files is what's the input to the program. The input in this case is multi-line text. This is a test, is only a test. I keep calling it carry on. And this has 3 lines, 14 words in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 61 total characters. Not going to count those. So this would be if this input was fed to this program word count, which counts characters, lines, and words, its output would look as such. So once you complete the Chester program, you could run it as follows. Have that completed program here called Chester. When you type make, it'll be produced. And then this little 2test.md file, that's in the testing or the data directory it's provided. You run Chester with that as your input file. And on the output side here, Chester will say, oh, I've got 2 tests in here. You've told me to run both of them. I'm going to run both of them. First one's done, second one's done, little dots here. And the overall results of this were the first test passed, it was okay. The second test passed is okay. So that's 2 out of 2 better there. So at any rate, we'll look at some of that stuff in a second. But if this feels familiar, it's very much akin to the make test business that you've had, which is provided by a script I wrote called testy, which has a similar kind of input to it, which has little headings that dictate tests and a bunch of options and expected input and output and so forth. And as well then can be run with a command like this to produce, this is how many tests you passed and failed, along with options like, oh, only run some of the tests and things like that. So if you want to get acquainted here, then please do have a look at some of that stuff. At this point, it will behoove us to open up and grab the TAST code so we can look at some of the data structures that are involved here and some of the functionality. So let me grab that. I'm going to zip back up to the top here to my P4 code. I'll copy that link address and buzz over to my Emacs. This is in a 216 sync directory, which a lot of you are prone to using. So I'll just issue a wget here to pull that thing down. And if I look in the directory, I got my P4 code here. So let me unzip that, P4 code.zip. And that should create a directory here, and we'll fish around a little bit. So there's a header file. We'll look at that in a second. There's this set of utility functions. These are provided bits of code. For instance, there's a splitting function, some initialization and deallocation functions, and as well this important parsing function that eventually you have to call along with some other things here. You should feel free to look around this one and poke it. Should require 0 changes if I did my job right. You may also look at the other source code that's provided here, but this one is just ridiculously gnarly because it's machine-generated code. In fact, one can compile other things into C code, and this is not an uncommon thing to do, and that's the output that's in this Chester parse here, produced by a PACCC tool from this parsing expression grammar that's in Chester parse.peg. Again, none of this stuff is stuff that you need to worry about terribly, just the fact that within the util, there's a parsing function, this init from file peg here that you may call in your main at some point. We'll maybe get to that a little bit later. Now, what I really want to do is to examine the data structures associated with this and draw them just a little bit, some correspondence to the input files that are over here. So on the left-hand side, I'm going to open up that data directory here where we can look at some of the input. For instance, here's that 2tests.md, and you can see my text editor knows about markdown files, .md files, and so formats them accordingly. And this looks a little easier on the eyes than the rendering that would appeared over there. That this basic bash test is highlighted here because this little hash means a heading. And then I can even sort of zip down to the second heading here, which is a word count. And as well, the code blocks here that appear between the little triple backticks, those are color-coded to indicate their proper markdown formatting. So we'll keep this up and then also look over here at the header file that's associated with this. This one's a bit long and has a bunch of things in it, but most of them you don't have to worry about. We'll instead sort of have a look here at the essence of what's at stake. So this entire file, this to-test.md, is going to be represented in the C program, or at least its contents, as a suite. And this is a common term that's associated with testing where you have a collection of tests that's to be run. They are a test suite. Some of them you may want to run, others you may want to ignore. And to that end, the suite encapsulates the entire collection. Its main feature is this tests array here, and we'll have a look in a second at the test struct like up here, but it's a big array. There's a maximum amount that can fit in it. And as well, then there's a little integer array that say, oh, here this thing has 3 entries, and they are index 2, index 5, index 9. That means there might be 20 tests in here, but only run 2, 5, and 9 in it. And hopefully you're acquainted with that particular facility that's provided in the testing framework they use for our programs. It's terribly convenient so that you don't have to run all tests if there's only one that's of particular interest to you. There are a few other oddities here. For instance, the suite will track a testing directory where the output and results associated with the testing is supposed to be put, and as well a prefix for all of the files related to this testing regime. These two things can be specified in directives at the top or near the top of the testing input file. You can see here prefix, that's 2 tests, so that would by the parser be filled in for this little prefix here, and the tester here, the parser, as it reads through this file, will create this struct and then fill in this little tester here with the string tester2test or test2test or something along those lines. And so when I run this, then that directory would be created. I don't have the working executable right now, but we may do that in just a minute here. So each of the things in the file then has some corresponding element in a struct over here. Now, I say over here, and I'm pointing at the suite that's yonder, but rather each of the individual tests then will have features that are associated with one of these buggers, test T. So up here, then each test is represented as well by a struct, and you can see this one's even bigger. It has a lot of fields associated with it. But these will include things like the title of the test, that's what appears here on the little blue line, a description of the test, that's what appears here in the multiple lines that appear after the title but before anything else. There'll be certain things like what program to run, which program is to be tested. In this case, that's set via directive here, but it's like bash in this case with these options and WC over here. And the parser, as it goes through this file, will fill in then this field within a test key struct for you. As well as, oh, here's input for this one. This previous test has no input, so this thing will be null. And then the output that's expected in each case, which is obligatory. So tester is a tester here, and this 31461 down here for the second test. So you can imagine there'll be 2 entries then for this testing file in the test directory here. The first one will have this title, the second one will have this title. The first one's program will be this bash here, the second one's program will be WC, and so on and so forth. Now, a bunch of the other fields that are over here are things that we filled in during testing. For instance, the input that's read out of this input here needs to eventually be fed to the program, and a convenient way to do so is to create a file that has this input in it. And then when you launch a child process that's going to execute the WC program, redirect to say read from this. And as well as you run either of these programs, you'll need to capture output somehow. And a convenient way to do that is say, hey, child process that I have launched in order to run these, redirect your output rather than on the screen, which will create a lot of mess. Rather, put it into some output file. And the output file name here in file name are things that your functions will fill in. I'll start talking about that in a second. Eventually, once the child process is done, and so you can imagine, oh, the child process is going to have up the ID, it's going to be running for a little while, it's going to exit, and I'll have to capture what that exit code is, and then read in what actual output it produced and compare that to the stuff that's in here. That's, if it matches this, we're good. If not, then the test fails. So to that end, each of these things has a place and is manipulated by the various functions that you'll define as we get into the crux of that. But understanding the basics of like, oh, here's and input file, and how some of that data gets transmitted into the running C program and reflected in structs that appear over here. And then others of this data that show up will need to be adjusted over the course of the run of Chester to say, I ran some tests, I figured out, yay, they passed, nay, they failed. This is how many total tests have passed and stuff like that is par for the course, what you're going to be up to. One final note, there's a little oddity in here, an enumeration, which C provides. This is sort of a glorified bunch of integers, but they're given symbolic names here, and there's just a modicum of type checking that can be done. So there's a field down here that's the state field, and tests basically start out as not run, or once I launch a child process for it, it should be running. Once the child process is done, we'll assign either it's passed or failed based on whether the exit code matches the expected value and the expected output is matched against what was actually produced over there. If those two things match up, then it's passed, otherwise it's failed. But you'll see the use of those symbolic names throughout rather than the actual integers that they are encoded as in binary. This is pretty common, and then something to be aware of. There are a few other defines up here that are worth knowing about, like the fact that on certain kinds of failures, you should return some exit codes that look like this and some tistis here, and maybe I'll mention that as we talk briefly about the functionality that's built in there. Okay, with that stuff at play then, you might sort of notice over here that, okay, there's a bunch of files in here, testing, etc., but I am missing some right now. And back over here, looking at the manifest, these two, Chester Funcs and Chester Main, those are the two that you'll need to create in order to facilitate the program development. So if you were to try to run any tests, for instance, right here, we test prob1, for instance, then you'll see immediately like, okay, there's no chesterfuncs.o that's needed. That's going to come from a chesterfuncs.c file, and that just is not present right now. And so we'll just create it. If you're curious like what's supposed to go in there, then I turn your attention down just a little ways here. There is a long outline of the functions that are supposed to be in this file. And similar to what we've done before, we'll take this outline and copy paste it in, fill in some of the definitions here just with stubs to say return -1 in a lot of cases, but that'll allow us to start running the tests that are over there. Now, each of these functions are here. They're divided per problem. So like the first 4 or so are part of problem 1. We'll talk a little bit more about that. And then you move on to some problem 2 functions. And then as we go on, let's see, this is problem 1 should really be problem 3. I'll maybe fix that in a second. But progressing onwards down here, the final problem is to write a main function that will be not in this funcs file, but in Chester main.c. And so we'll create both those so you can run all of the tests. That should get us off to a splendid start. I'm just going to grab a little bit at the end here because I know that if I hold shift and click up at the top, that'll highlight this entire thing, which is what I want. I'm going to do a little copy there, zip back over to my editor, and create a new file. We'll call this chesterfuncs.c, and then paste that puppy in. And we've got a sort of working version of this to begin with. Now, as usual, these are stubs. And so down here, I'll need to fill in these little semicolons here with something like, this is obligated to return an integer according to the return type. So I'll return -1 here. And for those of you who are, modestly advanced, you might start to do something like, oh, each of these things ends with a semicolon. And so I'm going to do a find replace. Let's see, replace the closing paren semicolon with a closing paren, opening paren, return -1 semicolon like this. And I'll say, yes, replace that, replace that, replace that, replace that. Not these. Yes, yes, yeah. Nope, sorry, not that one. And then I'll have to reinitiate that. Not you, but you, yes, you, yes, you, yes, you, yes. And main isn't in here, so okay, we're good. Now I'm pretty sure this is not going to type check, right? Because some of these actually are like, oh, like this is a void. I'm not supposed to return to -1, but I'll get rid of that there. And this is, horrendous style. That doesn't meet the style guide. So eventually I want to, carry these down. But hey, this will enable me to at least run the tests here. So let me come back over then and try a make test prob one. I'm in the wrong directory, so we'll go to P4 code here, make test prob one. Let's see, this is at line 178 because it's a void function and a void function for print window again. So let me come back here. That was 178. So I'll just nix this to become a void again. And try that one more time. Hey, look at that, already running the tests. I expect all of them to fail right now, but hey, that's that. Now, the very last set of tests for problem 5, they'll also whine and complain because there's no main function here. That is easily rectified. Let me come over here. I'll make a Chester main.c. Here's an int main, int argc, car star argv, return 0. Done. Does nothing. And so I could even like run the final test cases over here. But basically that's all the file creation that's needed. And now the hard work of actually filling in function definitions should begin. So let's preview just a little bit what you'll be up against on this. And I'd encourage you to look possibly at this outline over here, but also the individual use cases are here, or sorry, individual problems are defined here with some additional details about what's to happen in each of the functions, along with then the header associated with each of them. I should also say that right above this is the sample usage, which is worthy of study so that you know precisely where you're headed. And we'll maybe have a look at this in a second to see how this pans out. But this is a nice sort of synopsis of what's Chester's capabilities out of the box, or when it's finished should be. So the first problem primarily concerns getting acquainted with some of these data structures and creating just a little bit of sort of infrastructure using some system calls to sort of do some setup. So the first function, for instance, is associated with creating the testing directory. If you look back up here at a run of Chester, so the make, and then I'll run this for test business, then you'll see for this for tests, there's some intentional failures here. And so this output looks similar to what you've likely seen throughout development within this course, that there are 4 tests that are run, numbered irritatingly from 0, but no matter. 2 of them pass, but some of them fail. And the results then for those failures, as well as the successes for that matter, they're described in the subdirectory for this results business here. The top of this, let's see, where is it? So the top of this testing file for tests has a couple directives, or a single directive in it, and maybe I'll pull that up over here. So this is part of the data file it's printed. So there's 4 tests here. You notice it only specifies a prefix of 4 tests. And if I zip back over here, that's why each of these results files, number 1, number 3, associated with the test here, they start with 4 tests. The default directory to plop things down is Chester test. And there was no directive up top to say no, make a differently named directory. And so the header, or the suite struct here, as the parser sort of creates it, it'll create it so that this tester is the string Chester test. There might be a directive that alters that, so it would create a sort of different name associated with this tester. But in this case, the default is used. And so all of the results files and so forth, they'll be in this Chester test and then named for tests. Result 1, result 3, there's also result 2 and result 0 because those passed, etc. there. And as you'd want to know results, then you'd go into that Chester test directory, look for things that are called for tests, and then all the results are called this over here. So the point of this first function then, this create tester, is to create a directory that is named after what this tester field is in the suite. Now, if you are recollecting, you're probably not, well, I mean, unless you're really good, you might not remember, like, okay, how do I do that? But if your instinct is, oh, there's probably some kind of a system call that would allow me to do that, maybe I'll consult some documentation or some lecture slides or things like that, then that's the right instinct. And what you find by perusing is, oh, there is one. It's called McDir. And so you'd want to buzz around and sort of get a sense of what's involved with that one. There's some prescriptions here about if that directory already exists, you shouldn't attempt to recreate it and say let it be. But if a file named what you're trying to create exists, except it's like a text file, then it won't be possible to create that directory. And this function should bail, should report an error. So you'll likely use the stat system call to say, hey, is there any such file existing? If so, is it a directory? All's well then. If it doesn't exist, I'll make it. If it does exist, but it's not a directory, then I'm kind of in a pickle because I don't want to get rid of any file that someone has that's named that, but I can't proceed with the tests, so I'm going to bail at this point. And there's an associated error message that's associated with that. So just sort of quick hint here, if we went over to the funcs part here, and I zip back up here to this create test history, we'll just take a pot shot and do something like McDir. Let's see. I don't know. Let's call it the sweet arrow tester, and then I'll return 1, something like that. Now, this is by no means complete, but it's at least a sort of like facsimile. I'm not error checking to see if this is correct. I'm not checking to see if any files are around there, but I may as well give this a quick whirly gig. This will be for a test for problem 1. Oh, and I have no, let's see, too few arguments. Okay. I'd want to maybe look up what the arguments are, but I'm also just going to take a pot shot and put a 0 here and see maybe something along those lines. And hey, look, I got one of the tests to pass out of the way. So, this is the Goomba form of programming. Just throw some stuff at the wall and see what sticks. Sometimes appropriate, but you could probably start to refine this right now, just with a little bit of reading about McDir and what its options are like and so forth. Okay, so I think that's enough sort of discussion as its first function. Next few functions do things like, copy a string over to the suite associated with a particular test number. And maybe a lot of these functions that deal with an individual test within the suite here. And part of the reason that those two are coupled is that for a particular test, the output name is going to be associated with what's the testing directory and what's the prefix for the suite. So you need information from the suites to dictate fields of the test over here. But making use of that and a little bit of stirdoop along with getting acquainted with the sprintf family of functions. There's a sprintf and an sn printf. You should feel free to use either of those. Those will be allow you to sort of knock this kind of thing out very readily. The create infile, because it's really just creating a string, keep allocating and so forth. The infile does the same thing, except you actually have to create some input files if it's associated. So as an example over here, that 4 tests thing that we're looking at, no, it's actually the 2 tests here. The second test here had an input, and so I'd want this input to be shuffled into some directory that is under the testing directory. So 2 tests or Chester test or whatever else over there. So that when the child process is launched, it can be reading from the input file here. That it's hard to set up a string that's like that. Possible, but hard, but very easy to set up IO redirection involving a file that's on the file system there. So that's the essence of this creating input files part of the problem. And then finally, the converse of that is once a test is complete, somewhat later in this directory, there'll be an output file, and you'll want to slurp all that stuff in and populate the output actual field associated with that. So here. So these are just basic file operations, creating directories, opening files, reading and writing to them, and so forth. So there are things that we've talked about in lecture that you'll have studied in labs and homeworks already, and so it shouldn't break anyone's brain too much. The real crux of the project of Chester is to initiate tests to run in a child process. And this is handled mainly in the starting tests and finishing tests portion here. So there's a suite start test that says, whatever test is numbered here, test number 5, start that up. Launch a child process for it, have that child process redirect its input and output to appropriate files, and exec some program like bash or word count or something like that to test whether that program is behaving correctly. So that initiation there is what's responsible for the test start. Now that should create within the test struct, then it should fill in this little child PID to say there's now a child process running, a word count or a bash or something like that. It's going to produce outputs in this output file name. It's going to read input from this in file name here. And eventually you'll need to wait on that child process to populate its exit code over here to see if that matches an expectation. Sometimes you run programs and you expect them to fall flat because they're set up to fail. And, checking that they fail gracefully is part of the effort here. But oftentimes these expected exit codes will be 0, except if overridden with a directive. So a lot of things can go wrong with this. For instance, on initiating the child process, maybe you try to exec and there's actually no program named flubar on this system. And so there's a prescription for, in such failure cases, what you should do to return. But generally speaking, this will split Chester into a parent and child process, the parent being Chester itself, and will quickly return after that. Whereas the child process, if it's doing things right, will never return from this function. It'll eventually exec or exec a child process or exec a new program that's to be tested or return from this with some sort of error function. I should say not return, but exit of this. And this will be a chance to exercise the little exit C standard function, which rather than returning for a function, will exit a program entirely with the exit code indicated here. And these are defined in the header file, so make use of it there. This part of never actually returning from this function if you're the child process is really important, because if a child process does return from it, chances are it'll be in some sort of a loop that is then going to try to execute additional child processes. And so you'll create a tree, which is not at all desirable. Chester works in a fan, as in there's one Chester process, and it fans out child processes that run beneath it, generally waiting for the first leg of that fan to finish before launching a second and then launching a third, and waiting for each of those to finish up. Although one of the makeup problems that's planned will be to launch multiple child processes and monitor the progress of all of them at once. The counterpart to starting a test is finishing a test. Slightly counterintuitively, this function does not make a wait system call. Instead, it's to be used after a child process is actually finished. So what's passed in here is a status of this is what was returned from a wait system call on this, which was implemented later. And this basically finalizes all the data associated with the test. Did it pass? Did it fail? Does it have output that needs to be read in? If so, do so and fill this field in and set its end state to be either failed or passed. So this is not a terribly long function and just deals in with utilizing some of the previous functions to read in inputs and as well, or sort of read in the output from the test and then evaluate, does that look appropriate? Third problem involves creation of test results, and there's a lot of I/O involved. To make this slightly easier, there are two little utility functions that you'll write that do a bit of string processing. The first is to take a string, this little string out here, and for a particular position, print out a little window around that position according to the left-right width that's given here. To make this slightly more flexible, there is an output stream that's provided. Generally, this will be the results file that's being produced, but you could redirect it to the screen as well in that. So the print window examples down here just sort of indicate like, oh, here's this F right here, print a window of like 3 around it, so that would be the or 2 around it, that'd be the DE, 2 to the left, and GH, 2 to the right. Some more examples here, including clipping that if I want a window of 4 around B, I can't go beyond the first character, and if I start at K here, I can't go beyond the end of the string. Now that's used in results by saying, hey, check these results and find the first spot that there's a difference between them. So here, if this was my expected results, but here there's a difference in it, the differing index function allowed me to find like, oh, here there's supposed to be a 4 and there's an X instead. So the output that was expected does not match the actual output. So print a little window around this to help someone who's trying to debug that program identify this is where the problem occurred. So those two functions then are used in conjunction in the big sort of results file function, this sweet make results file. And this is supposed to produce output that informs on the behavior of what became of this test. In this case, you can see some test number 6, it failed. It was titled as such, and there's a big capital fail here and also at the end. The description and title are printed. The program that was run was printed along with inputs. And then in this case, the failure happened because there was a mismatch between the expected output, which was 10.10.21, and the actual output, which was 10.9.20. And so this makes it apparent to anyone who's debugging that program what's happening here. Now, your purpose is to produce this output file, and there's a big gnarly sort of output function here, a sweet test make results file with a ton of documentation associated with it. Basically, it's, okay, go through and print parts of this completed test out. Its title, description, program, the input, the output, the exit codes. And within here, then, like as you look at the expected and actual output, this is where you would use, this differing index function to say, this differs at the index 3 in those strings. Let's count. There's the 0th, the 1th, the 2th, and the 3rd. There's a 1 here and a space here, or 9. I think it's a space there. And so that third, that's the first spot that's different. And then you print a window around that according to some parameters that are specified in here. So this is not quite as nice as the side-by-side diff that a lot of you are accustomed to in the testing regime that we provided. However, it's sure a lot easier to code. And I know from personal experience, because unless any of you want to code up a Needleman-Wunsch algorithm to solve the dynamic problem of finding the longest match between two sequences, then yeah, this is much easier to do than that. So if you're curious about those things, come talk to me and we'll walk through some of the testing code, but let me do this first up there. So this is a bit of a monolith of a function, but output functions that produce reports like this are very typical of that. But there's quite a bit of documentation in the doc string here about what to do, the name of the file, the general ordering of the sections, what to do by way of if there's a mismatch in the output, if there's a mismatch in the exit codes, and so forth. Finally, then, if you get to the fine art of actually running the test suites, the required function to do this, run tests single proc. The single proc means run one test at a time. So launch a child process to run it, wait on that child process, and then if there are more tests to run, launch the next test in a child process. Wait for that one and come back. This isn't the most efficient because if a particular test takes a while to run, because I/O bound, or if you have multiple cores, it'd be nice to run in multiple processes. And that's one of the plan makeup problems that I'll probably have ready for you by tomorrow. But at any rate, this is relatively easy to do and involves use of previous functions. It's a loop, so iterate over the tests that are to run, not necessarily all the tests, just the ones that are to run, and be cognizant of the fact that there's an array that indicates these are the indices of the tests in the suite to actually run versus running all of them. So just do a sort of start test, wait on that, and then call the finish test part. Print out a little dot at each time you finish a test, along with a done at the end, and voila, all tests are run, and you have hopefully accumulated results for it, as you call that finish business, know where they pass or fail. And there's a little tag on function here that will say, within the suite, print out the results table here. That's sort of nicely formatted. And this will give you a chance to use some printf capabilities to, for instance, say, this is in a width of 2 here, so that if I get 10 or 20 tests, then they'll line up nicely. And these things are printed in a nice string width of 20 or so that the OKs and failures over here line up and so on. Finally, then, the last part of this is to actually create the main function. And let's see, the main has a couple different forms that you can make use of. There's a bit of advice here about how you might start main to say like, I've got some input file. I'll establish a stack variable for my suites and then call the provided initialize that suite from a file over here as such, maybe checking for errors. But this is generally what's needed then to set the main up so that it reads stuff from like a test.md. It'll be your chance, though, to do a little command line processing to say, I could run Chester either by default here, where all of the tests in here, perhaps all 20 of them are run, or specify additional command line elements to say, I'm only interested in test 2, 5, 9, and 11. Load the rest of these from the input file. That's what this function will do. But set the suite up so that that test to run array only has these numbers in it. So you'll have to do a little bit of command line processing to figure that part out and make it happen. The output associated with the main run will be things that look like following and run like this, where I'm running these special cases, but only running 247. Then it'll print out, this is the file that's being run from, the word running, and then 3, this 1, 2, 3 tests here out of the 9 possible that are in that testing file that to be run. And then at the end, overall, that's 2 out of 3 pass, along with stuff in between that was previously demonstrated. That'll be stuff like, oh, print out that I'm running these in the progress, and as well like the little test table that's down over here. Now, I neglected to mention, no, I think I mentioned that enough. Like a lot of the strings are duplicated, but no matter there. So the grading criteria of this are divided in half as usual. There are 50 test cases spread across the 5 problems. And they're 1 point a pop, and then various manual inspection criteria that I added this morning to this, so that you get a little bit of advice about how to code style and so forth. One big mention is that the staff have put together a C coding style guide, which will be used to assign the credit for the code style for this project. So we don't have any individual rubric items here on things like indentation and commenting and so forth. Rather, you'd want to pull up this style guide over here to get a sense of that. Importantly, if you are a VS Code user, there's some ways that you can configure your VS Code just so that you can just click a button or click a menu item, and that will auto format all the code to adhere to one of the accepted coding standards. So this has information like, we'll accept 2 or 4 spaces. Please note 8 spaces, it's just a bit wide. We'll accept the Google style, parens up here, or the Microsoft style, parens, beneath. Either of those is fine in my book, although I tend to favor one versus the other. Comments like throughout, keeping things not too wide, etc. And then this auto formatter setup if you're using VS Code. Most editors that are worth their salt will have some way to say, take this entire region and indent and adjust the curlies to according to some standards. And VS Code is no exception to that. There's little rules that you can put in here to say, like, the Google style or the Microsoft style, how many spaces to use for indentation, 2 or 4, etc. So adjust that to taste. Just make sure that do not program like Bob down here. Bob's code will lose major style points because it's inconsistent in curlies, inconsistent in indentation, lack in comments, etc. So don't be like Bob, as the saying goes. All right, the only thing that remains on the project is that there will be some makeup credit. I just haven't had a chance to describe what exactly that looks like right now. Generally, the plan is to have 2 makeup elements there. The first is that you may write a parser for the input files that is your own thing. This has to be a hand parser in C, and so you can then utilize that in your main program to parse things in. Some test cases hopefully associated with that. That'll probably be about 10 makeup credit. And then another 10 makeup credit if you would like to write a multi-process running algorithm. So as opposed to the, let's see here, problem 4 where we're running single proc, this will be a multi-proc that honors one of the fields in the suite that says use a maximum number of processes in order to complete this stuff. Something like 4 or 8, that's usually tied to the number of cores that you have on your machine. And this will hopefully get the suite of the tests run faster as it will utilize those hardware resources to run in parallel the tests. Again, those will be makeup credits and should be on the table within the next day or 2, along with test cases and descriptions and so forth. All right, I have blabbed far too long about this. The project, while it looks a little bit long, is not tremendously long in its scope. It plays out very nicely in terms of implement this function, implement this function. There'll maybe be a few gotchas, but generally things stack very nicely. And what you'll have at the end of the day is a real-world program that can run other programs and evaluate did they behave correctly according to an expectation or not. And along the way, you learn quite a bit about what you use system calls like open and read and writes and stat and fork and waits and dup2 and so forth. So this one feels real good from my perspective. I know it won't feel real good while you're doing it, but hopefully by the end of it, you'll feel that Chester was well worth the effort and taught you. That's it for me for the moment. I'll see you all in lecture tomorrow, and happy hacking until then.